All right, guys. So today's lecture is the first of a two-part series on variational autoencoders. Some of these slides that I'm going to be presenting today and in the next class are owed to Dan Schwartz and Tom Manzini. Schwartz's name should be spelled with a Z, I think, not an S at the end. Anyway, what we've seen so far, we've seen neural networks, how neural networks can perform classification or even regression, like MLPs, CNNs, and recurrent neural networks. We've seen how they can generate data from Boltzmann distributions. Those are Boltzmann machines. Now we're going to look at them as generic generative models, how they can model the distribution of any data such that we can draw samples from it. So, but first, before we begin talking about it, what is a generative model? That is the primary question that we're going to be addressing is about how you can train neural networks to be generative models, but what is a generative model? And what is the standard procedure to estimate them? One of the most popular techniques is expectation maximization, and what we will be covering in this lecture and the next is going to draw on ideas from EM. So let's go over what a generative model is first. A generative model is a model for the probability distribution of any data. For example, a multinomial or a Gaussian. The characteristic of a generative model is that it's a model. It's almost as if you can computationalize it. And in fact, in many cases, you really can. So the computational equivalent of it would be a model that can be used to generate data with a distribution that's similar to your given data X. So you can imagine having a magic box of this kind, which is your generative model, and you would feed it a seed, and it would generate some data. And every time you fed it a seed, it would generate data. And eventually, if you looked at the distribution of all of these data, it's going to be very similar to the distribution of the data that you're trying to model. And just to be facetious, where does the seed come from? That seed would have to come from some other model, which in turn is also going to look just like this. And that model would have a seed. And so that seed would come from some other model and so on. So where does that chain end? It turtles all the way down. Anyway, that's just being facetious. The point is, a generative model is a model for a computable model for the distribution of data. So for example, a multinomial probability mass function. Now, if you have discrete data of this kind, where the data can take only one of a discrete set of values, then the simplest kind of distribution is where the number of values it can take is finite, like rolling a dice. In that case, the way you would model the distribution for the data is as a multinomial distribution, where each of the outcomes has some probability. This distribution can actually be expressed as a probability table. On the other hand, if you have a discrete data set, discrete data where the data can only take discrete values, but the number of values it can take are infinite in number. For example, if you said your data can be any positive integer. Once again, these are discrete data, but the number of possibilities is infinite. Now you can't just store their probabilities as a table. You need some kind of a formula for it. And so you would need a parametric form, like a Poisson distribution, the formula for which is given over here. It has a parameter, in this case, lambda. And in order to compute the probability that your outcome is going to take any specific value, you just plug that value into this formula. Or if your data have continuous values, then once again, you would need some kind of a formula. It's a model, so it's a computable model. You have some kind of a formula, like in the case of a Gaussian, the formula looks like what you've had here. The equation itself has, the model itself has a small number of parameters. For the Gaussian, it's going to be the mean and the covariance matrix. And once you have those, given any x, you can compute the probability that that x could be observed. So when I'm speaking of learning a generative model for data, here's the problem. You're going to be given some set of observed data, some collection X. This is the data whose distribution you want to model. You're going to model it with a generative model. you will choose a model, P of x semicolon theta. Now again, as I said, this is a computable function with some parameters, so theta represent the parameters. And then we're going to estimate this theta such that this probability model given by this function P of x semicolon theta best fits the distribution of the actual data that we are trying to characterize. And we will generally estimate these theta such that this model best fits your observations that you're using to learn the model. And the hope is that once you learn it, it's also going to represent data outside the training set. Now, this is all old stuff, nothing new for you guys. But let's continue with this anyway. So let's consider the case of multinomials, just to give you an idea of how this thing works. Let's say some guy's rolling dice, and then you rolls the dice a large number of times, and eventually plots a histogram of the outcomes. So these this is histogram with 6 bars shows you a histogram of the number of times each of these 6 outcomes occurred. 1 occurred n1 times, 2 occurred n2 times, and so on. Now, of course, this is a discrete random variable. This is a discrete variable. It takes only 6 discrete values, so the probability distribution is a multinomial. Now, if I were to give you a choice and say that the actual distribution of the data is one of these 2 guys to the right, which of these 2 would you choose? Anyone? Someone there? Can you guys hear me? Yeah.
Second
one. Pardon me?
I raised my hand, Advait. It's my turn.
Okay, you guys are being recorded. Which one?
I'd like to choose the green one.
Okay, why?
Because it looks more like the left one than the top one does.
Correct. It fits better, right? Here's another example. Here's a histogram of a collection of observations. In fact, these are real data. These are log energy values for a speech sample I once analyzed. And now I want to compute, let's say, the probability distribution. I want to characterize the probability distribution of log energy of speech based on these data. I decide that this shape looks like what a Gaussian would give me. So I'm going to use a generative model. I'm going to model this as a Gaussian. I have a number of different Gaussians that I could fit. So the red one, the green one, or the yellow one. And once again, which of these 3 would you choose? Anyone?
The red one looks like a good fit.
Yeah, so again, how do you define a fit in this case? It looks visually like a fit. I know, at least one of you is going to jump in with the answer. So before you do, let me answer it myself. Now, you chose something, you want to define a best fit. And the way you choose, we can quantify this visually. Of course, the fit is obvious. The fit is obvious because the data that are more frequent are being assigned higher probability by the one that you chose. The observations that are less frequent are being given lower probability. So this definition of fit is can be quantified through the notion of maximum likelihood. The maximum likelihood principle states that the data are generated by draws from the distribution. So if the generating process draws data from the specific distribution for the data, we also assume that the world is a boring place. So the maximum likelihood principle can also be restated as the world is a boring place principle. And what this means is that anything you observe is typical. It's very typical of the process that you're trying to characterize. So we're going to, in fact, take the world is a boring place assumption to the limit, and you're going to say that the data that you observed are about as typical as you can get. So the distribution for the actual distribution of the data has a very high probability of generating whatever that you observed. This isn't necessarily true, but this is the maximum likelihood assumption. The world's boring. And so you select the distribution that has the highest probability of generating the data, which means it should assign lower probability to less frequent observations and vice versa. So going here again, exercising the maximum likelihood principle, consider these 2 cases. In one case, I got draws from a discrete draws of a discrete random variable where the variable can take only one of 6 values. In the other case, it's a continuous valued variable. And in both cases, I've plotted histograms of outcomes. Now, the maximum likelihood principle says that if I'm given these data, I'm going to choose some model P of x semicolon theta as the model for the distribution of these data. Theta are the parameters. I'm going to choose the theta that maximizes the probability of the data that I have observed. And typically, rather than just maximizing the probability, we will maximize the log probability because the log is a monotonic function. And so the argmax of a log, the log of a function is going to be the same as the argmax of the function itself. And so these estimation problems would be restated as follows. For the multinomial case, here there are 6 possible outcomes. So there are 6 parameters to estimate, P1 through P6. And the log probability itself, yes, Chris?
So you said that we use the log space because it's monotonic, but you didn't really explain why we use the log space. You just...
I'm coming to that to the next one, right?
Gotcha.
So consider this multinomial over here. This has 6 parameters. And if I assume that uppercase X represents my set of training instances and that they're all independent, then the total probability of my training data is going to be the product over all X of the probabilities of the individual X's, and I'm taking a log. So also in the case, so this term that I'm circling with the laser pointer, we want to estimate the probability parameters such that this term is maximized. Similarly for the Gaussian, once again, if capital X is my set of training instances, which are all independent, the total probability of my training data is going to be the product over all instances of the probabilities of the individual instances. I'm going to be maximizing the log of this term with respect to the parameters of the Gaussian. Now, why log? Because, but before I get there, what are these terms? Consider this, I'm going to simplify these first. In the case of the Gaussian, P of x is simply the probability specified by the Gaussian. I could just plug in the Gaussian formula here. In the case of the multinomial, this term, if I have 1,000 observations, there are only 6 possible outcomes for each of these 1,000 observations. So I could group these observations by the values. So I can rewrite these formula like so. The probability of my set of observations can, in the case of the multinomial, can be written like this: is the product over all possible outcomes of the probability of the outcome raised to the number of times that outcome was observed. In the case of the Gaussian, it's simply the product over all observations of the Gaussian computed at that observation. And now let's look at y log. Yes, Yesh? What's the question?
Earlier, I represented the index over samples, right? For it was X. Okay. So I goes from 1 through 6, is it?
I goes from 1 through 6 over here.
Okay, sure. Yeah. Okay,
right?
thanks.
And so now the problem is, if you were just directly maximizing this term inside the parenthesis, you have a product of many, many terms, and that kind of maximizing the product of many, many terms, it can be complex. But when I take a log, this product term is going to become a sum. And so this product over all outcomes pi raised to ni, if I take the log of this guy, this is simply going to become summation I pi raised to ni, summation I log of pi raised to ni. And I'm having trouble with the mouse as always. And once again, this further gets simplified. It's going to get summation of I ni log pi. So you can see how just taking the log over here simplified this ugly looking term to something that's much simpler over here. And so also for the Gaussian, if I took take the log, this product is going to become a sum. And so the overall optimization is simply going to be these problems here. In the first case, I would try to maximize this term, the sum over I of the Ni times the log of Pi, which is, you know what this is. The point is that when I actually maximize this, you get the familiar estimate for the probabilities for the various outcomes, which is the proportion of times that of the observations where the observation took the value of that particular outcome. So the probability of 1, for instance, is going to be the number of times 1 occurred divided by the total number of observations. So also, if I were to maximize this guy over here, with respect to the mean and variance of the Gaussian, you're going to be maximizing the sum over all observations of the log of the Gaussian. And if you work out the math, you're going to come up with the familiar formula. The estimate for the mean is simply the average of the observations. The estimate of the variance is the average of the squared, centered and squared samples. And that's not the point here. The point, this maximum likelihood estimate itself is fairly simple. The point I was trying to convey was that what we are trying to do is to estimate the parameters of our generative model to maximize the likelihood of our observations. But then you can end up with this situation. Sometimes the data provided may be incomplete and therefore insufficient to estimate your model parameters directly. And this could be because the data themselves have missing components, like data vectors have missing components, or because of the structure of the network that should have been modeled, like mixture models or multi-state generative models. So let's consider this first example to see what this could mean. Let's say you have a collection of vectors and you want to model the distribution of this collection of vectors as a Gaussian, except that when you were recording these vectors, some components of these vectors got lost. So this could happen, for instance, if you were running a census and somebody refuses to report their income or to tell you their ethnicity or things like that. So you would have all of these vectors where you observe several components, but some components are missing. And the components that are missing in different vectors could be different. You have to estimate the mean and variance of the Gaussian from this data. So what would be a good way of doing this? Now, the original problem, if you had all of the components, that's what I will call the complete vector, where there are no missing components. Then the way you estimated the parameters of the Gaussian was to maximize the log of the complete set of observations, which is simply maximizing the sum over all observations of the log of the probability of the individual complete vectors. The problem here is that we don't have complete vectors. So you cannot compute this P of X because you don't have X. What you have are just these components. You have sets of incomplete vectors comprising only the observed components of the data. These components are missing. All the terms, so the observed components here I'm representing as O1 through ON. The O1 represents the vector of observed components. So also here the missing components I'm representing as M1 through Mn. M1 represents the vector of missing components in the first vector. Or in general, Mi is going to be the vector of missing components in the ith vector. So since every vector has both observed and missing components, the complete data are in fact going to be the union of the observed and the missing components. So the complete vector in any vector, in any observation, is going to be the combination of both the things that you observe and the things you couldn't observe, except of course the things that you couldn't observe are unknown. The missing components are missing. And now, if you want to use the maximum likelihood principle, you can make no observation, no assumptions about the things you didn't observe. The only things you have are the stuff that you observed. So that means you want to maximize the log probability of the data that you did observe. And that's all you really can do. So the maximum likelihood estimate is going to be argmax over mu and sigma squared in the case of the Gaussian of the log of the probability of the set of observed vectors, which again gets decomposed over here as the sum over all of the individual vectors, or the log of the probability of the set of the observed components in each vector. The problem is, once again, you can't really compute P of this little o, because the Gaussian is defined on the complete vector, which includes both the observed and the missing components. So we have to derive this P of O, which is the probability of the observed components, from the probability of the complete vector. So here's how I can do this. The probability of any complete vector with observed and missing parts is going to be the probability of the joint of the observed and missing components. So if I want to do, because X is simply the union of O and M. So if I want to compute the probability of just the observed components, I must integrate out, marginalize out the missing components. So I'm going to integrate P of X over M from minus infinity to infinity. Basically, I am integrating the joint probability of O and M over M. I'm marginalizing out M. The outcome is going to be P of O. So the log probability of the entire observed training data is simply going to be the probabilities of is simply going to be the sum over the entire data training set of the probabilities of the individual components of observed vectors, or the log probabilities of the observed components of individual training vectors, which is going to be the log of the integral of the joint probability of O and M over M. So as you can see, the actual maximum likelihood estimation problem in this case is going to be this ugly formula to the right here, which is going to be maximizing the log of an integral of an observation, or of a probability, where the specific, so not only do you have this horrible problem where you're trying to maximize the log of an integral, the specific components that you're going to be integrating out could change from vector to vector. So this entire optimization doesn't have a closed form. Any formula where you're trying to maximize the log of an integral is challenging on a good day and impossible on a bad one. So here's one problem. You get the idea of what I mean by missing data and how they can cause problems. Now here, in maximum likelihood estimation. So this was the first case where components of the data are themselves missing. You can have other problems where there's some information missing because of the structure of the model. Again, this should be model, not the network, like in mixture models or multi-state generative models. So consider this. Consider a Gaussian mixture model. A Gaussian mixture model is a generative model which assumes that the data assumes this structure for the generative process. It assumes that data are generated through a two-step process. It assumes that you have a number of different Gaussians at your disposal. Each Gaussian has its own mean and variance. In the first step of the process, you're going to select one of these Gaussians according to some distribution. Now, because you have a discrete number of Gaussians, the process of selecting one of these Gaussians is the process of drawing from a multinomial distribution P of k. Once you select the Gaussian, the actual observation O is drawn from the Gaussian that you have selected. Now, the probability of obtaining any specific observation should be obtained by considering all of these guys. So now a Gaussian, any of these Gaussians is capable of generating this observation O, because the span of a Gaussian is from minus infinity to plus infinity. So the probability that you're going to get a specific observation O is the probability that you will choose the first Gaussian, and that Gaussian will generate O, plus the probability that you will choose the second Gaussian, and that Gaussian will generate an O, and so on. So it's going to be the sum over all Gaussians of the probability of choosing the Gaussian times the probability of generating that particular observation from the Gaussian. And so if we have this model as the generative model of our data, we have to estimate all of the parameters of this model, which is called a mixture Gaussian, because you're mixing a bunch of Gaussians. in order to learn the distribution of the data. Now, observe here that if this is your generative model, the model that's shown in the dotted box, the process of generating a single observation actually draws two random variables. In the first step, it draws the Gaussian. In the second step, it draws the observation from the Gaussian. So the probability of a particular draw is actually the joint probability of both variables, the probability of choosing the specific Gaussian that you chose, and the probability times the probability of generating the observation that you got from the Gaussian that you chose. And of course, when you write this formula out to the right, you're actually marginalizing out this first variable because you're not privy to the entire drawing process. You only see the outcome. Oh, exactly which Gaussian was chosen is hidden from you. It's latent, which is why you get this formula. It's a sum over all Gaussians, or the probability of choosing the Gaussian times the probability of generating the observation from the Gaussian. Now, if I'm given a collection of training data and I have to learn all of the parameters of the Gaussian, of this Gaussian mixture, ideally, this dotted box would be a glass box. I would see exactly what was happening in drawing every single observation, which means that for each training instance, assume that you have a mixture of 3 Gaussians, which are represented by colors over here. If you wanted to learn the parameters of this observation, of this distribution, and if you had a glass box for the generative process, then for every observation, not only would you see the actual vector that was produced, but also know which Gaussian was chosen when that vector was produced. So if this set of data, which is in the observation vector itself, and the identity of the Gaussian that generated that particular observation, that's what is a complete set of data that characterizes the entire process of generating the particular observation. If you had that information, then estimating all of the parameters of the Gaussian mixture is quite trivial. To estimate the parameters of the blue Gaussian, you're going to simply segregate out all of the vectors that were drawn from the blue Gaussian. And then you can just estimate the mean and variance from this set of vectors. So also to estimate the parameters of the red Gaussian, you'd simply segregate out the vectors that were drawn from the red Gaussian. And then you can compute the mean and variance of the Gaussian from this set. And so also for the green Gaussian, very easy. The problem is, when you actually get the data set, that box is not a glass box. You cannot see how the data was generated, so you do not know which Gaussian generated any particular vector, which means we are missing information. Our data are incomplete. What we want is the combination of the observation and all the intermediate variables that were also drawn when producing the observation. In this case, the identities of the Gaussians. What we got was just the observations. And so here is the maximum likelihood estimation. You're only given the observed data. You have to estimate the means and variances of all of the Gaussians, and also the multinomial distribution with which the Gaussians are selected, but I'm not going to, I'll ignore that for now. So the problem we have, the maximum likelihood estimation problem, is the problem of estimating the log probability of all of your observed data, which is the problem of estimating the parameters to maximize the log probability of your data, which is you want to estimate all the means and the variances of all of the Gaussians such that the log probability, or the sum over all of the training instances of the log probability of the individual training instances is maximized, except of course the probability of any individual vector is a mixture Gaussian. So you end up with this maximum likelihood estimate where you're trying to maximize the log of the sum of a bunch of terms. And again, anytime you have to optimize the log of a sum, this defies direct optimization becomes really hard. So in all of these cases, you have a general form of the problem. You have your data are either missing some components or some key variables, and these must be marginalized out of your probability by summation or integration. And so this results in a maximum likelihood estimate of the form where you're trying to find some parameters which maximize the log, the sum over all observations of the log of this of a marginal probability, which is to say the log of a sum of probability terms. And it doesn't have to be sum here. This could be an integration, as in the case of the Gaussian that we saw earlier. And here I'm explicitly showing you that the model has these parameters theta, which is why the theta is written here. And this log of a sum or an integral makes this estimation very challenging. There's no closed form solution, and we need efficient iterative algorithms for this purpose. So after this slide, I have an entire collection of slides on explaining the expectation maximization algorithm. I'll sort of, I've hidden these slides. Maybe I would have had time to go over it, but anyway, the gist of it is that when you have problems of this kind can be easily enough solved using the EM algorithm. And the summary of the EM algorithm, I recommend that all students actually go over the slides in which I show how the EM algorithm works and how these formula are derived, because it'll appear in the quiz. And the summary of this algorithm is that we are going to construct what is called an empirical lower bound, or an elbow function, which is a function of two sets of parameters. One is the expectation maximization algorithm is an iterative algorithm, and this function, the first set of parameters is the current estimate of the parameters. The actual variable are the parameters themselves. So and this theta. The empirical lower bound has this structure. Instead of having a log of a sum, it converts the log of the sum to the sum of the log. This elbow function sums over all observations, the sum over all possible values of the missing components of your data, of the posterior probability of the missing values, computed using the current estimate of the model parameters, times the log of the joint probability of the missing values and the observed data. This is the complete data given the parameters we'd like to estimate. And a second term, which is not really a function of theta, so you can ignore it. This function, and as you will see from the slides, if you iteratively maximize this function j theta theta k, you're guaranteed to get an ever increasing log likelihood for the observed data. And so you get an iterative hill climbing algorithm for the maximum likelihood estimation problem. The actual estimation looks like this. You're trying to maximize over theta, j of theta times theta k. Once you find the theta that maximizes this j, you set that to theta k plus 1. You stick theta k plus 1 over here. You get a new function j, you maximize that again, and repeat this process. So the entire expectation maximization algorithm looks like this. You're going to initialize, it's an iterative algorithm, you initialize your parameters, and then you continue these two steps until the log likelihood of your data converges. In the first step, you compute the posterior probabilities for the missing components, for all values of the missing components, using the current estimate of your parameters for every single observation in your training data. That is the expectation step. Then you have the maximization step, where you now compute this elbow. You use these values to formulate the elbow function, which is the sum over all observations of the sum over all missing values of the conditional probability of the missing values given the observation and the current estimate of the parameters times the log of the complete data given the parameters. Now, this is also much math. And anybody who's taken any of my lectures knows that I like to throw math at your face, but then I don't really use it. I like to explain things with pictures. So I'm kind of assuming that the math went over many of your heads. What you really want is an intuition. What is the intuition between how EM solves the problem? So let's look at this first problem first. This is the case where the data have missing components. When the data have missing components, here is the problem again. You have these data. Here is an example problem. You have all of these vectors. You're trying to estimate a Gaussian distribution, but the vectors have missing components. So the actual data we have are just these green components, that is O, comprising a sequence of incomplete vectors. The missing data, which is given by M, is a sequence of missing component vectors, which I'm representing by M. The complete data includes both the observed and missing components for every single vector. Now, let's go back and let's consider just say the first vector, right? Any one single vector. This vector, here's your first vector. You have all of these green components. You're missing this black component. So the question, we don't know what it is. So here's a question I'm going to ask you. If I have a very large number of these vectors with this component missing in every single case, so if I then, so just assume that we got a very large number of draws from this Gaussian, and from this Gaussian, from those draws, we segregated all of the guys for which these green components were identical to the corresponding observation that we got. So in that collection, what would you expect these missing components to be? So these are all complete vectors that have been drawn from the Gaussian, and these complete vectors match the observed components exactly. So in that set, what are these missing components likely to be? Now, anybody want to answer that question? Over here, guys? Yes, Yash?
Yeah, it's going to be similar to the other vectors, because if all of the other components are the same, then it looks like those vectors should be very similar. So you can just pick up that missing component from the other vectors that you've observed.
So, but I'm asking you, it's not that. The question is, I've drawn a very large number of these guys, okay? So I've gone to this Gaussian and I've generated a giant number of vectors, and then I've selected all the ones which are identical here. My question is, in that giant collection, this is still also going to be a very large collection. What are these values going to be, right? And there's no guarantee. These are all not going to be the same value. They're going to be different values. They're all different draws, right? So if you actually saw this, you're going to see yes, Abraham?
It will be the mean of the values?
It wouldn't be the mean. These are all draws from this Gaussian, right? You're going to see every single possible value, any value at all that this guy can take. You're going to see in this. You're going to see in this set. Would you not?
Yeah.
Right?
Yes.
Exactly. But you're not going to see all of them in uniform probability. Some values are going to be more frequent than others. Correct?
Yeah.
And what would that be? Any possible value M is going to occur in proportion to the probability of M given O, because you're fixing the green components. So the variation in the missing components is going to follow the conditional probability of the missing components given O. Make sense?
Mm-hmm.
Right, Chris, does that make sense to you?
It does.
Yeah, okay.
Yeah.
So here's what we're going to do. I'm going to complete this incomplete vector by filling the missing component with every possible value. I'm going to make an infinite number of clones of this incomplete vector, but I'm going to assign this missing component in proportion to the relative frequency with which I expect to see them in the distribution, which is P of m given O. And I can compute P of m given O if I have Px, because Px is the joint of O and m, right? And so here's what I will do. I'm going to expand every one of these vectors out and complete them by filling in these missing components in every which way possible, but in appropriate proportions, proportional to P of m given O. Does that make sense? Guys?
Yes, it does.
Yeah, that does make sense.
So, and now, where exactly does this P of m given O come in? This is expectation maximization is an iterative algorithm. This will come from a previous estimate of the model. And now, once I have this expanded set, I'm going to compute the statistics from this expanded set, right? So we can go over the formulae. Let xi of m be the completed version of oi when the missing components are filled with value m. So for every one such column, I'm going to get a different xi of m. These are all the completed vectors xi of m composed from oi. These are all the completed vectors xi of m. These are all the completed vectors of x1 of m from O1. These are all the completed vectors x2 of m from O2 and so on. I get this large collection. Yes, Chris?
So in general, you're just saying it's like a weighted average.
There's no weighted average. I'm actually explicitly expanding it out, right? It will come out as a weighted average, but you know, but you have to be very careful. It's not a weighted average, and you will see this in a minute, right?
Okay.
Let's say I have this complete set of expanded observations. Okay. And now I'm going to use this complete set of expanded observations to compute the mean of the Gaussian. What will happen? Then you're going to see the first m guy, the first value of m in proportion of P of m given to O, correct? The second, here I'm doing an integral because there are an infinity of m's. A Gaussian is a continuous random variable. So if you actually work this arithmetic out, the average of any component over here is simply going to be, this is the complete vector. Xi of m is the complete vector. Do you see this? Right? But xi of m is going to occur in proportion of P of 2, P of m given, this should have been OI. This notation is slightly broken. Does this make sense to you guys? So this first term over here is simply the average of all of the vectors in the first bundle, or not even the average, the sum of all of the vectors. Yeah, I can think of this as the proportional sum of all of the vectors in the first bundle. And if I took O to be the first box, if I took O to be the incomplete vector that constructed the second box, this is going to be derived from the second bundle. But the point is, it's the average of xi of m. I'm basically computing the average of this larger collection of vectors. That is the mean. If I want to compute the variance, I'm going to compute the average of the outer product, the centered outer product of this large collection of vectors, the expanded collection of vectors, which is this guy here, weighted by the proportionality. And I'm summing over all of the observations. Does it make sense? Anyone?
Yeah.
Yep, makes sense.
Right. So basically the point here is that you're expanding the data out in every possible way. And now you're computing your statistics from the completed data. And so the overall algorithm is going to be something like this. You're going to initialize your Gaussian. And then at each point, you're going to be completing your vectors in every possible way and creating this expanded data set, computing means and variances. Skip the formula. The concept is important, right? I have this, I've expanded it out by completing the data in every possible way. I compute the means and variances from this completed data. And then I go back and use the completed data to re-estimate these posterior probabilities, because when the parameters of my distribution change, the manner in which I complete the data is going to change. And I keep repeating this process till it converges. Now, this was for the case of a simple problem of trying to estimate a Gaussian from data with missing components. Let's consider the second one, where I don't have missing data components, I have missing information, like in the case of the Gaussian mixture. So here, again, we have all of these vectors, but we are not told which Gaussian each vector came from, so our data are incomplete. We only have the observations. What we really want are the observation and the identity of the Gaussian from which the observation was drawn. And we know that every single Gaussian is capable of generating this vector with different probabilities. So what we will do is ask ourselves this question. If I saw a very large number of these vectors, how many of them would have come from the first Gaussian? How many of them would have come from the second Gaussian? How many of them would have come from the third Gaussian? These numbers are going to be in proportion to the posterior probability of the Gaussian given the observation, correct?
Yep.
Yeah. So, make sense to all of you?
Yeah.
Yeah. So, I'm going to complete this data. I'm going to assign it to every single Gaussian, but so basically I'm making many clones of this data, but I'm going to assign it to each Gaussian in proportion to the posterior probability of the Gaussian, which can be computed if I know pk and pfo given k, right? And now I'm going to use this completed data to compute my parameters. So these guys here, which are needed to compute the proportions, come from a previous estimate of the model. So here's what the actual EM for Gaussian mixtures is going to look like. I'm going to expand this first vector out in every possible way. I'm going to complete the data where every possible way of completing it is completed in proportion to the posterior probability of that particular possibility. So the blue completion over here is going to have a proportion which is the posterior probability of blue given this vector. The red completion over here is going to be in proportion to the red Gaussian given this vector, and so on. And now I'm going to compute the statistics from this completed data over here. I'm always computing statistics from completed data. And once I have completed data, it's very simple. If I want to compute the mean and variance of the blue Gaussian, I'm just going to segregate out all of the blue vectors from these sets. To compute the statistics of the green Gaussian, I'm going to segregate out the green vectors. For the red Gaussian, I'm going to segregate out the red vectors. And subsequently, I can just compute the means and variances of these Gaussians. Now, again, observe that I'm actually factoring in the proportions over here, right? This vector over here is going to be assigned to blue in proportion to P of blue given observation. See? So I'm just factoring in the proportions over here. And this is going to be the mean of the blue Gaussian. Each vector, the first vector is going to be assigned to the blue Gaussian as in proportion to blue given O. So this is the weighted average. But then if I want to compute the variance, this outer product term is computed from a vector which occurs in this proportion. And so you're not taking a weighted average of the vectors and then computing a variance. No, you're computing the variance of this expanded set, right? Or the segregated data from the expanded set, which is to say you're taking the outer product of these vectors and computing their average, where in the process you're naturally going to account for the proportions in which they occur. That gives you this updated formula. Did this make sense to you guys? Over here?
Yeah,
Yes.
I have a question. So like, it seems like you need an infinite number of these vectors.
So the point is proportions, right? So conceptually, the way I've explained it, I'm saying it sounds like you need an infinite number of these vectors. But then if I blow these things up in proportion by infinity, it's not going to change this formula. If I blow all of them up in proportion. So the proportionality constant basically disappears. You just need to consider the specific outcome and factor in the posterior probability. The proportions take care of that. Just think of this guy, right? Suppose instead of having just 5 of these examples, I had 5 trillion examples. But this first vector is going to occur a trillion times. The second vector is going to occur a trillion times, and so on. Because these bottom guys are the same, all you change, right? This formula itself will not change. The trillions are going to get canceled out in the numerator and denominator.
So how do you know how to sample correctly?
I'm not sampling. Here I'm actually explicitly filling it up, completing it, right? So I know the formula just comes out. I'm saying that for this first vector, if I had an infinite number of these guys, 2/3 of them are going to come from the blue. So I will have something over here which is going to say, just imagine a very large number, n. So n times 2/3 are going to be here, right? Of this vector, say 1/3 we're going to come from the blue. So n times 1/3 are going to come here. It doesn't matter what n is simply going to get canceled out. You have a very good question, right? But if this number n, the samples I'm drawing, are going to infinity, it's just going to end up being this expectation, right?
So you're assuming that you already know this underlying proportion.
I'm saying this is where the iterative algorithm comes in.
Okay.
I'm going to start off by assuming I know the parameters. Based on the parameters, I'm going to compute the proportions. I use the proportions to update my values.
Okay, that makes sense.
Let's go back and do this, right?
Yep.
Make sense?
Mm-hmm.
We had a very good question about the sampling. Why? Because it turns out it's going to affect us. But here's the general EM principle. I'm going to complete the data by considering every possible value for the missing data or variables in proportion to their posterior probability given the observation, which is the probability of the missing components given O, or the probability of the Gaussian given O. I'm going to re-estimate the parameters from these completed data. That makes sense, right? But then, as you mentioned, I don't need to complete this in every possible way. I could actually take something simpler, right? I don't need to complete the data by considering every possible value for the missing data or variables. I could be sampling the missing values from the posterior to complete the data. And you expect to get the same kind of behavior, right?
Yep, makes sense.
Makes sense? And so here's the alternate EM. This is the EM that you always learn about when you learn EM in any machine learning class. Except they don't actually explain it this way. But then the sampling, when you look at it as completing the data, it also naturally follows that you could be simply sampling the missing values. And that's still going to be just EM, right? You're completing the data by sampling the posterior distribution. So here is the overall EM principle. You're going to have to remember this. Initially, some data or information are missing. You're going to initialize your model parameters. Then you're going to iterate this. First, you would complete the data according to the posterior probabilities, either by explicitly considering every possible value with its posterior-based proportionality, or by sampling the posterior probability distribution. And then using this completed data, you're going to re-estimate the model. And so this is the complete iteration. This is the EM principle. Questions? Okay. So I'm going to switch gears.
I had a small question about EM.
Yeah.
So in maximum likelihood, usually you said that we get a closed form solution of the parameters. And
I'm not saying you get a closed form solution. You very rarely do.
Oh, not
maximum
even
likelihood is a principle, right?
Right. For like the case when you had complete data, you're saying that it would be easier to find a closed form solution.
It might be easier. In many cases, it's easier. Yes.
Right. For EM, can we be guaranteed that we get the right solution by just this iterative principle?
No, because what you're doing is you're iteratively completing the data, right? You're iteratively completing the data in every possible way, and you're using this to estimate your re-estimate your parameters. Now, this, if you go through the slides, this guarantees that from iteration to iteration, the likelihood increases. It doesn't mean you're going to find the global optimum.
Right. So like neural networks, this would depend upon your initialization.
This would very, very much depend on your initialization.
Sure. Thank you.
Right. Questions, guys? No. Okay. So now I'm going to switch topics. Oh boy. I have 26 minutes left. I'm going to run over. But anyways, everybody knows what principal component analysis is, right? You want to find the principal subspace such that when all vectors are approximated as lying on that subspace, the approximation error is minimal. And here I'm going to assume the data are centered, zero mean. This assumption is not really it's not critical, but especially for the problem setting we'll be looking at later. But for now, let's assume this. So what does this mean? I want to find this subspace in the case of two-dimensional data. I might want to find the one-dimensional subspace, which is just a line, such that when I project all of the data onto the subspace, then this results in the lowest total squared error. In each case, the error is the length of this line. And I want to find this blue line such that the squared sum of the lengths of these green lines is minimized. That's PCA. All of you remember this, right? So here it is. If you are given some data of this kind, you want to find the principal subspace such that when all vectors are approximated as lying on that subspace, the approximation error is minimal. So here, for example, if you approximated every vector as every black vector, black dot, has its corresponding red dot, all of which lie on this line. This particular line is the principal axis, which ensures that the squared lengths of all of the errors, which are shown by the thin black lines, is minimized. And the way you do it is you're going to sort of search through all possible lines until you find the one for which the squared sum of those lengths is minimized. This is how PCA is performed. You guys remember this, correct? Anyone? Questions? The
data is centered because we're considering lines that pass through the origin, right?
So though the data are not centered, you can do the same operation for data that are not centered. The distinction is going to be whether you're trying to between capturing most of the variance in the data versus most of the energy in the data. The distinction is kind of immaterial for this lecture, but it's actually key in other problems. It just turns out that you can think of the centering as a bias term in a neural network, for instance, right?
Sure.
So you can ignore it for now.
So,
but this, yeah.
Why are the lines only passing through the origin always, the ones that we're considering?
Because the data are centered. They're zero.
Okay. Okay.
Zero,
sure.
Right?
Sure. Yeah.
So that's right. Okay. So this is what we're considering. Okay. Now you can actually do this in closed form. You're trying to minimize the squared L2 error, right? So I'm going to assume this line can be represented by a unit vector. I'm going to assume that the line is represented by this vector W, which is unit length. It doesn't have to be unit length without loss of generality. Any vector on that line represents the line, but I'm going to assume that it's unit length. And so if I want to find the closest approximation on the line to any given vector, what I'm really doing is projecting the vector down to the line. And the length of this projection is simply the inner product between X and W. And it's going to be X transpose W divided by length of W for the generic case. But if I assume that W is unit length, then I can just say this length is X transpose W. So the actual vector itself is the actual projection is going to result in an error. This error is going to be the squared error, which is the squared length of this dotted line, is going to be the difference between the squared length of this blue line and the squared length of this projection. And by Pythagoras theorem, that's going to be the norm of x squared minus x transpose w squared, which I can write out. So this is nothing novel here, right? When I'm projecting a vector onto a line, this is the error that's going to result. Doubts here? Can't be. So when you perform principal component analysis, this should have been a transpose, something got messed up. You're basically summing this squared length over all of your training samples, and you're finding the vector w such that this length is minimized. And if you solve it subject to the constraint that w is a unit vector, you get the familiar eigenvalue equation where you say that the w must be an eigenvector of the correlation matrix. Comes out very cleanly. This is no. How many of you are not familiar with PCA? Anyone? I guess not, right? So these things are sort of follow. Now, there's also an iterative solution. In the case of now again, our objective is to find a vector subspace W and a position Z on W, or such that or a length Z on W such that Z times W approximates X as closely as possible. So W is the unit vector, Z is this length. And so this vector, this is a vector, right? So the actual vector position is going to be Z times W. And you want to find for every vector, you want to find this unit vector W, and for every X, the corresponding length is Z, such that for every X, Z times W is as close as possible to X itself. That is the problem, correct? Now, suppose I have a collection of training samples. I can put all of those collection of training samples into a vector, into a matrix X. These lengths Z, they're actually kind of position vectors. In the case of a line, it's just going to be a length. But if these were three-dimensional data that you're projecting onto 2 dimensions, Z is going to be a 2-component vector in any case. So these position vectors for all of the training data, I can put into another matrix, uppercase Z. And what our problem is to find the set of bases W and the corresponding position vectors for all of our training data, such that W times Z approximates the set of training data itself as closely as possible in an L2 sense. Now, this is the actual PCA problem, and I can do this in an iterative manner. Instead of trying to solve the eigenvalue problem, I can do this way. I can fix W and then estimate the Z's, the positions. Then I can fix the positions and I can estimate the W's. If I repeat this process, it's kind of guaranteed to find the principal subspace. Let's see this with pictures and you'll see why this works. Here are some 4 points. I want to find the principal subspace. I'm going to initialize the subspace, which is the basis W, which is going to be this line shown over here as my initial estimate. Then I'm going to find the position on this line that is closest to each of these guys. So this I can do by simply projecting these guys down onto this line, right? Having done that, what this really does is individually minimizes the squared lengths of the lines from the point to their approximations on the line. You see why this is happening, correct? Now I'm going to sort of attach these red dots to the line. Once I've dropped these black dots onto the line, you know that this has in some sense minimized the squared length of all of these little black dotted lines. Now I'm going to sort of attach these red dots to the line. I'm going to attach the other end of these dotted lines to these black dots. And then I'm going to release the red line. I'm going to let it rotate and shrink and rotate and stretch. What would happen? Do you think it would stretch or not? Anyone? Would it rotate? Guys, anyone? So what would happen here? Think of these lines as having some tension, right? The tension is proportional to the squared lengths. These guys are going to try to decrease. So they're going to pull this portion of the line up. This guy is going to try to decrease, is going to pull this side of the line up. This guy is going to try to decrease, is going to try to pull the line down. And so eventually the line is going to sort of swing up into this shape, with these red lines being the attachments. The line is allowed to rotate and stretch. So you're going to, so the relative arrangements of these points will stay fixed, but the spacing can change as the line rotates. And the new line is going to end up in this position with these guys as their attachments. Did you see what happened here? Anyone? Abraham, Chris, anyone?
Why aren't the errors the perpendicular distance in this case?
Can you repeat that, Abraham? It was not.
Why aren't the errors the perpendicular distance? I see.
So here is what. So this is an iterative step. In the first case, I have dropped the lines onto the. I've individually shortened the line. So which means that now these red dots are allowed to move on the line. And so when the red dot is allowed to move, each dot is going to come perpendicularly below the black dot.
Yeah, here I get it. But
now I
next
attach
one,
the red dots and don't allow them to move together. The line is allowed to rotate. So you're jointly minimizing the total squared length of the lines from their attachments to the plane.
Oh, okay.
And that's going to give you something like this, right? Second step.
Yeah.
Now I'm going to release the red dots and let them slide. And they're going to do that. That's going to be the new position, right? And now I fix the red dots. What will happen is, since it's a joint, the whole thing is going to go to that position. Right.
Okay.
And then I'm going to release the red dots and they're going to fall down to this position.
Makes sense.
Chris, does that make sense to you?
Yeah.
Yeah. So this iterative algorithm is kind of guaranteed to eventually come to a point where these guys don't want to move and the line 2 is happy. So it will give you the principal subspace. And it's an iterative algorithm for PCA. In fact, if you have very large amounts of data, you can't be computing correlation matrices and eigen decomposition. So it actually uses algorithm. So I tried to animate the whole process and I got this really horrible. It neither shows what I'm trying to show nor looks pleasant, but I put it anyway. Now, let's take a cartoon view of what iterative PCA is doing. I'm initializing this W. Then in the first step, if I have the W, I have the pseudo inverse of W. And from the pseudo inverse of W, I can compute the Z, which is to say I'm finding the position on the plane for each Z, for each X. And then once I have the position on the plane for each X, this is done individually for each X. I'm going to fix this set of Z's and the axis. I'm going to adjust the W, which is to say I'm rotating the plane to minimize the error to minimize the error between W, Z, and X. So this cartoon view of PCA is this two-step process where you get the Z's from all of the X's. This is where you're estimating the Z's individually for the X's. And then you fix the Z's and then you estimate the W to make the output as close to X as possible. This is really what's happening in PCA. Make sense to you guys? The iterative step? And you keep iterating.
How do you estimate the W in the second step?
So that's the formula here, right? I can, I'm given, this is just a pseudo inverse. I'm trying to say WZ approximates X.
Right.
If I fix Z, then Z is going to be pseudo inverse of W times X.
Right.
It's a least squares estimate. That's it.
Right. So
and then if I fix Z, it's going to be W equals X times pseudo inverse of Z.
Okay. Computing the pseudo inverse of Z, that is not computationally challenging for a large number of vectors, is it?
It is, but this I'm trying to convey a principle over here, right?
Sure, sure.
Okay, but this is what you could be doing. And pseudo inverses are actually, you know, there are efficient ways which depends only on the dimensionality of the data, or the lower of the two dimensions, the number of vectors or the dimensionality of the data. Anyways, but the point is, you see what is happening here, correct? I can redraw it like this. I'm passing x through pseudo inverse of w to get z, because and then I'm going to be multiplying z by w to get back x. This figure, does it look familiar? This is like an autoencoder with linear activations. You have the forward pass, which gives you the hidden representation, the encoder pass, and then the decoder pass, which gives you back the input. Doesn't this remind you of a linear autoencoder?
Yep.
Yeah.
Right? So what you do when you actually train a backprop, train this thing using backprop, is that instead of stepwise first adjusting z and then adjusting w in giant steps, you sort of incrementally simultaneously update both z implicitly and w in tiny increments. But this is what a linear autoencoder is. So there's one small issue. This whole thing is kind of scaling invariant. So for example, this, if w is unit length, then z represents this length and this point is zw. But if my basis is of a different length and it's now w prime, then I'm going to have to multiply it by a different number to get back to the same point, right? So I can increase the length of w and correspondingly decrease the scaling factor z to end up at the same point for the approximation, which means that the solution is not unique. I can increase these z's and increase these w's and shrink the z's, and the net result is still going to be the same. To give you a better idea of what this means, consider where my principal subspace is 2 dimensions. And here are 3 examples. In each case, the principal subspace is the same. In the first case, I chose these 2 red lines as my bases, w1 and w2. Then, to represent this vector v is going to be some a times w1 plus b times w2. So the z vector, the position vector z is going to be ab. Instead, if I chose these 2 bases, w1 prime and w2 prime, then this same position vector, same vector v is going to be some a prime times w1 prime plus b prime times w2 prime, because the bases have changed. The amount by which you have to scale each of these to get to this point also changes. So now for this new set of bases, the position vector becomes a prime z b prime. Instead, if I had some other basis vectors like these guys, w1 double prime and w2 double prime, then the vector v is going to be some a double prime times w1 double prime plus b double prime times w2 double prime. So the position vector is going to be a double prime b double prime. So in all cases, the actual gray plane is the same, the point is the same. All that changed was the bases that I was using to represent the plane. Both bases lie on the plane. I can take any 2 bases, any 2 vectors on the plane, and they'll form a basis. And depending on the basis I choose, the manner in which the position vector z that I use to represent this point changes. So the subspace is and these guys are related. This one is going to be a linear transformation of this. This is going to be some other linear transformation of this. So this entire representation is invariant to linear transformations of the position plane, of the position vector. If I transform the position vector, I can find a corresponding set of bases. That makes it work. So the subspace is invariant to transformations of z. Does that make sense?
Yep.
Right? Yeah.
Yep.
So this means the solution is not unique. Once again, right? So there are 2 ways of finding a solution. You can either require the vectors in W to be unit length and orthogonal, which is what you use in standard closed form PCA. Here you're putting an imposition on W. Or I can put an imposition on Z and say that I want my position vectors to have some kind of a standard distribution, 0 mean unit variance. So depending on which option you choose, the W's you estimate are going to be different, but the principal subspace is always going to be the same. So let's look at the second solution, which is what is of real interest to us. I'm going to be, sorry, I should have been focusing on this. I want to constrain the variance of Z to be unity, right? So if I use the autoencoder format, all I can say is that I want to use this autoencoder, but in between I'm going to impose a unit variance constraint on Z. And if I impose a unit variance constraint on Z, it still is going to find the same subspace, but the solution is going to be a little more unique-ish. I can run the algorithm 2 times and expect to get 2 solutions which look somewhat the same as far as Z is concerned. The question is, how do I actually impose this unit variance constraint? So to understand that, let's go back and take a look at what PCA really does, and look at it from the iterative algorithm perspective. Now, you're saying that all of these vectors can be very closely approximated by their projections on some subspace. Now, the projection on some subspace is characterized by these position vectors on the subspace. If I knew these position vectors, I can find the subspace uniquely, correct? But I don't know these position vectors. So I have to find both the position vectors and the subspace. So what we did was we initialized the subspace, the plane, or rather the basis for the plane. Then these position vectors were missing. We completed the data by computing the appropriate Z's for every one of these vectors for this plane. Then use the complete data to go back and re-estimate the plane, and repeated the process. Does this look familiar?
It looks a little bit like the EM algorithm.
Yep, right. This looks familiar. It looks like EM. In fact, it is EM. But if it is EM, there must be a generative model. What is the generative model and what distribution does it encode? So it turns out that imposing the constraint that Z must have unit variance over here is the same as saying that Z is being drawn from a standard Gaussian. It's like saying Z has a standard Gaussian prior. So if I say that Z is being drawn from a standard Gaussian distribution, then this block, this is just a block which takes in a Gaussian random variable and linearly transforms it. This is just a generative model, right? This trailing end of this, the decoder of the AE. So in fact, linear autoencoders have a generative story. When you project all of these points onto some hyperplane, what you're saying, the generative story is that there is a hyperplane, there is a principal subspace. You first take a Gaussian step on the principal subspace, and then randomly, and you're going to get to some point. And then you're going to take a second Gaussian step orthogonal to the subspace to actually generate the point. This is the generative story behind PCA, and so, or linear autoencoder. So this is what the generative story behind PCA is, that you have some data, that you are drawing some data from a standard Gaussian, putting it through a linear transform, which is this process is the same as saying I'm taking a Gaussian step on the principal subspace, and then I'm adding some noise which is orthogonal to the principal subspace, and the noise is Gaussian, which is the same as saying I'm now going to take a Gaussian step off this principal subspace. So this guy here is the generative story for PCA. Z is drawn from a k-dimensional isotropic Gaussian, where k is the dimensionality of the subspace. Here it is 2. And then this is being transformed by some linear transform A, where A actually represents the basis for the subspace. The matrix of principal eigenvectors or bases for the principal subspace. And then subsequently, you're adding a noise E which is Gaussian, but is only allowed to vary orthogonal to the subspace, which means that the Gaussian is low rank, right? And so what PCA actually does is to implicitly obtain the maximum likelihood estimates of A and D from training data. That make sense?
Yep.
Yeah. So this is the generative story behind PCA, that the decoder weights are just the basis matrix. Remember, we saw this autoencoder figure, and this was the decoder in the representations lecture. That decoder is really just is this linear transform. You have some Gaussian going in, and you're adding some noise. So the decoder weights over here are just the PCA basis matrix, and the encoder weights are simply the transform that you can use to compute the z's from the x's if you were in the process of learning this model. But this upper end is the actual generative model. So the encoder transforms x into the Gaussian z, and the decoder transforms the Gaussian z into the principal subspace reconstruction x hat, and then you add the orthogonal noise to actually get your data x. And so the overall thing is this: if z is Gaussian, a linear transform of a Gaussian is going to give you a Gaussian. So x hat is Gaussian. You're adding a Gaussian to this x hat, so x is Gaussian. The distribution model by PCA is a Gaussian. The PCA model assumes that the observed data are Gaussian. They lie very close to a linear manifold, which is your principal subspace, plus some noise, which is orthogonal to the subspace. So this is the kind of distribution that PCA actually models. But then there's an assumption over here. The actual assumption here is that the data consists of some Gaussian. Yes, Chris?
Are there other models that model other distributions other than Gaussian?
PCA assumes Gaussian. You can do, well, we'll get to that, right? So the characteristic of the Gaussian is that it lies close to a linear principal manifold. And that's what PCA does. If you don't want that assumption, we're going to have to wait for Wednesday. But then here it is, right? So the PCA has one problem. It assumes that the data are generated by taking that the main component of the data lies on this linear manifold, which is the principal subspace, and that the noise are orthogonal to the subspace. So that in order to get any observation, you're going to randomly draw from this Gaussian data on the principal subspace, and then add some noise, which is orthogonal to the principal subspace. There's something broken about this assumption. In real life, noise is not orthogonal to what you want. Consider images. When I add noise to images, if I just pulled out the noise and looked at it, it could also look like a valid image, right? Or imagine sitting in a room where you're recording speech, you hear all of this buzz, that's noise. But if no one was speaking and you just closed your eyes, you could imagine you heard voices. Random noise can sound like speech. So assuming that noise is always orthogonal to the data is kind of broken. So let's generalize the model to permit non-orthogonal noise. That gives us something called a linear Gaussian model. I'm going to update the same model, but now I'm going to say that this noise E, instead of always being orthogonal to the plane, it's allowed to lie in any direction. The only assumption I'm going to make is that the noise is uncorrelated, which means the noise value in any direction is independent of the noise value in any other direction. The noise remains Gaussian. So the generative model now is to say I'm going to take a Gaussian step on the hyperplane and add a full rank Gaussian uncorrelated noise that is independent of the position on the hyperplane to get to the data. So when I say this noise is full uncorrelated Gaussian, it means that covariance matrix is diagonal and the direction is unconstrained. It can be orthogonal to the plane, it can even lie on the plane. And so this is the entire linear Gaussian model. The problem with this is it's kind of like PCA, but then something broke. In PCA, if I gave you the plane and I gave you the point, you knew exactly where on the plane the data was generated from. But now, because the noise can be in any direction, if I give you the point and give you the plane, you cannot be certain about where on the plane the data were actually generated from. Because the way to produce any data instance is no longer unique. I could assume different noises and attribute that observed data to any point on the plane. So nevertheless, this entire thing is still a parametric model for a Gaussian distribution, where the parameters are the basis of this plane and the covariance matrix of the noise that is added to the point on the plane to generate the data. So this entire model is known as factor analysis. The basis for the plane are what are called the loading matrix. The position vector on the plane are what are called factors. And the noise, uncorrelated noise, is characterized by a diagonal covariance matrix. These must be estimated. So this is where we will stop. What we've seen so far is that EM is an iterative technique to estimate probability models for data with missing components by iteratively completing the data and re-estimating parameters. PCA is actually a generative model for Gaussian data, which assumes data like close to a linear manifold with orthogonal noise. And factor analysis is also a generative model for Gaussian data, which assumes data like close to a linear manifold. It's like PCA, but without directional constraints on the noise. We'll continue with this and move on to VAEs in the next class. Questions, guys? Any questions? No.
No questions from me.
Good, let's stop recording.
Thanks.